NENOMATICA, where mathematics meets YouTube excellence. The seventh law of power. Here's our example. We need to find the value of the expression 0.25 raised to negative 2 power multiplied by 8 to the fourth power divided by 0.125 cubed times 2 to the negative 1 power. Let's start by converting the decimal numbers to fractions. 0.25 is equal to 25 over 100, and 0.125 is equal to 125 over 1,000. Now, let's deal with the negative exponents. Remember that when we have a negative exponent, we can rewrite it as 1 over the base raised to the positive exponent. So, 25 over 100 raised to negative 2 becomes 100 over 25 squared. Similarly, we apply the negative exponent rule to 2 to the negative 1 power, which becomes 1 divided by 2 to the positive 1 power, or simply 1/2. Now, let's simplify the fractions. 100 divided by 25 equals 4. And for the denominator, we can rewrite 125 over 1,000 raised to the power of 3. For the expression in the denominator, let's think about 1,000. We know that 1,000 equals 10 cubed, but we can also write it as 8 times 125. So, 125 over 1,000 equals 1/8. Raising this to the third power gives us 1 over 8 cubed. Let's rewrite the terms using powers of 2. We know that 4 equals 2 squared and 8 equals 2 cubed. So 4 squared becomes 2 to the fourth power, and 8 to the fourth power becomes 2 to the 12th power. Using the power of a power rule, we calculate 2 squared, squared as 2 to the fourth power. And 2 cubed to the fourth power becomes 2 to the 12th power. Now, let's combine the like terms in the numerator using the product rule of exponents. 2 to the fourth times 2 to the 12th equals 2 to the power of 4 plus 12, which is 2 to the 16th power. For the denominator, let's also convert to powers of 2. We know that 8 is 2 cubed, so 8 to the negative third power equals 2 to the negative 9th power. We can also write 1/2 as 2 to the negative 1 power. Now, we can combine the terms in the denominator. 2 to the negative 9th power times 2 to the negative 1 power equals 2 to the power of negative 9 plus negative 1, which is 2 to the negative 10th power. When dividing powers with the same base, we subtract the exponents. So, 2 to the 16th power divided by 2 to the negative 10th power equals 2 to the 16th minus negative 10th power. 16 minus negative 10 equals 16 plus 10, which is 26. So, our final answer is 2 to the 26th power. Welcome to this math tutorial. Today we'll solve a complex numerical expression step by step using the rules of exponents. Let's look at our example. We need to evaluate the expression, the quantity 0.04 squared times 625 to the negative second power, divided by the quantity 1/5 to the negative fourth power times 0.008 cubed. First, let's rewrite our decimal values as fractions. 0.04 can be written as 4 over 100, and 0.008 can be expressed as 8 over 1,000. Now, let's rewrite 1/5 to the negative fourth power. This is equivalent to 5 to the negative first power to the negative fourth power, which equals 5 to the negative first times negative 4, or 5 to the fourth power. Next, let's rewrite the expression to better work with the exponents. Notice that 100 is equal to 4 squared, and 1,000 equals 8 cubed divided by 8. 625 is 5 to the fourth power. Now, let's apply the power rules to further simplify our expression. We know that when a base is raised to an exponent and that entire expression is raised to another power, we multiply the exponents. So the quantity 5 to the fourth power raised to the negative second power equals 5 to the fourth times negative 2, which is 5 to the negative 8th power. Continuing our simplification, the fraction 100 divided by 4 equals 25, which is 5 squared. And 1,000 divided by 8 equals 125, which is 5 cubed. Now, let's apply the power rule again. 5 squared raised to the negative second power equals 5 to the power of 2 times negative 2, which is 5 to the negative fourth power. Similarly, 5 cubed raised to the negative third power equals 5 to the power of 3 times negative 3, which is 5 to the negative 9th power. Now, let's combine like terms. In the numerator, we have 5 to the negative fourth power times 5 to the negative 8th power, which equals 5 to the negative 4th plus negative 8th power, or 5 to the negative 12th power. In the denominator, we have 5 to the 4th power times 5 to the negative 9th power, which equals 5 to the 4th plus negative 9th power, or 5 to the negative 5th power. When dividing powers with the same base, we subtract the exponents. So 5 to the negative 12th power divided by 5 to the negative 5th power equals 5 to the negative 12th minus negative 5th power, which is 5 to the negative 12 plus 5, or 5 to the negative 7th power. Welcome to our lesson on exponent laws and simplifying complex expressions. Today, we'll explore how to solve expressions involving exponents using several key rules that will help us simplify even the most complex problems. Let's look at our first example. We need to find the value of 2 to the 7th power divided by 3 squared over 3 to the negative 2nd power divided by 2 to the negative 3rd power. To solve this, we'll work step by step. First, we need to rewrite the expression in a more manageable form. Let's begin by rewriting the division as multiplication by the reciprocal. When dividing by a fraction, we multiply by its reciprocal. Next, we'll multiply the numerators together and the denominators together to simplify our expression. Now we'll apply one of our fundamental exponent laws. When multiplying powers with the same base, we add the exponents. So 2 to the 7th times 2 to the negative 3rd equals 2 to the power of 7 plus negative 3. Let's simplify the exponents. In the numerator, 7 plus negative 3 equals 4. In the denominator, 2 plus negative 2 equals 0. Here's another important exponent rule. Any non-zero number raised to the power of 0 equals 1. So 3 to the power of 0 equals 1. Therefore, our final answer is 2 to the 4th power, which equals 16. Now, let's try a more complex example involving variables and multiple exponent rules. In this example, we need to simplify the expression a to the n raised to the power of 2m times a to the negative n raised to the power of negative n times a to the power of m squared, all divided by b to the m raised to the power of 2n times b to the negative m raised to the power of negative m times b to the power of n squared. First, let's apply another key exponent law. When raising a power to another power, we multiply the exponents. So a to the n raised to the power of 2m becomes a to the power of n times 2m, which is a to the power of 2m n. Let's apply this rule to each term in our expression. For the numerator, a to the n raised to 2m becomes a to the 2m n. Similarly, a to the negative n raised to negative n becomes a to the n squared. The term a to the m squared remains unchanged. We apply the same transformations to the denominator with base b. Now we can apply the product rule again to combine the powers in both the numerator and denominator since they have the same base. Looking at our expression, we notice that the exponents in both the numerator and denominator are identical. When dividing powers with the same exponent, we can rewrite this as a fraction raised to that common power. We can simplify this further by factoring the exponent. We have 2m n plus m squared plus n squared. This expression can be written as m squared plus 2mn plus n squared, which is actually a perfect square, the square of m plus n. Therefore, our final simplified expression is the fraction over b, all raised to the power of m plus n squared. We need to simplify this complex expression. We have a fraction where the numerator is the product of several terms with exponents, and the denominator also contains a product of terms with exponents. This entire expression is then raised to the power of negative 3. Let's simplify this step by step. First, we'll combine all the terms with the same base in the numerator. We have 6 cubed as the first term. Then for the terms we have a to the negative 3, a to the negative 2, a squared, and a cubed. When we combine these, we get a to the power of negative 3 plus negative 2 plus 2 plus 3, which equals a to the power of 0. Similarly, for the b terms, we have b to the power of negative 2 plus negative 2, which is b to the negative 4th power. Finally, we have c to the negative 3rd power. Next, let's combine like terms in the denominator. We have a to the 5th, 8 times a to the negative 6th, and 9 times a to the negative 3rd. When combining the terms, we get a to the power of 5 plus negative 6 plus negative 3. We also need to combine the coefficients. 8 times 9 is 72, so we get 72 times a to the negative 4th. For the b terms, we have b to the negative third power and b to the first power, giving us b to the negative third plus 1, which is b to the negative second power. Finally, we have c to the negative second power and c to the first power, combining to c to the negative first power. Now we can further simplify our expression. In the numerator, a to the power of 0 equals 1, so we can remove that term. The denominator now has 72 times a to the negative fourth power, b to the negative second power, and c to the negative first power. Now, let's convert this to a more standard form. We can move the terms with negative exponents. When we move a term with a negative exponent from the numerator to the denominator, or vice versa, the exponent becomes positive. So this gives us 3 times a to the fourth power times b to the negative fourth times b squared times c to the negative third times c. Now, let's combine the like terms again. We have 3 times a to the fourth. For the b terms, we have b to the negative fourth times b squared, which gives us b to the negative second power. For the c terms, we have c to the negative third times c to the first power, which gives us c to the negative second power. Now, we apply the negative third power to the entire expression. When we raise a product to a power, we apply that power to each factor. So we get 3 to the negative third times a to the fourth times negative 3 times b to the negative second times negative 3 times c to the negative second times negative 3. Let's simplify the powers. 3 to the negative third is 1 over 3 cubed, which is 1 over 27. A to the fourth times negative 3 is a to the negative 12th power. B to the negative second times negative 3 is b to the positive sixth power. And c to the negative second times negative 3 is c to the positive sixth power. This gives us a to the negative 12th times b to the sixth times c to the sixth, all divided by 27. So, our final answer is a to the negative 12th power times b to the sixth power times c to the sixth power, all divided by 27. Let's examine the following expression. We want to simplify the fraction. 25 to the power of 105 plus 5 to the power of 1 times 5 to the power of 2 times 5 to the power of 3, and so on, up to 5 to the power of 20, all of this divided by 5 to the power of negative 70 plus 5 to the power of negative 70. Let's start by rewriting the numerator. First, we'll express 25 as 5 squared. This will help us work with a common base in our expression. Now we can apply the power rule, which states that when we have a power raised to another power, we multiply the exponents. So 5 squared to the power of 105 becomes 5 to the power of 2 times 105, which equals 5 to the power of 210. In the numerator, we have a product of powers with the same base. Using the product rule of exponents, when we multiply powers with the same base, we add the exponents. So 5 to the power of 1 times 5 to the power of 2, and so on becomes 5 to the power of the sum of all these exponents, which is 1 plus 2 plus 3, and so on up to 20. Now we need to find the sum 1 plus 2 plus 3 up to 20. This is an arithmetic sequence, and we can use the formula for the sum of an arithmetic sequence. N times the average of the first and last terms, where n is the number of terms. In our case, we have 20 terms starting at 1 and ending at 20, so the sum equals 20 times the average of 1 and 20, which is 20 times 10 and a half, giving us 210. Looking at our expression now, we have 5 to the power of 210 plus 5 to the power of 210 in the numerator. We can factor out 5 to the power of 210. This gives us 5 to the power of 210 times 1 plus 1, which equals 5 to the power of 210 times 2. Now, let's look at the denominator. We have 5 to the power of negative 70 plus 5 to the power of negative 70. This is 2 times 5 to the power of negative 70. Now, we can simplify the fraction by dividing both numerator and denominator by 2. When dividing powers with the same base, we subtract the exponents. So 5 to the power of 210 divided by 5 to the power of negative 70 equals 5 to the power of 210 minus negative 70. Subtracting negative 70 is the same as adding 70. So we have 5 to the power of 210 plus 70, which equals 5 to the power of 280. And that's our final answer, 5 to the power of 280. Let's quickly recap what we did. First, we rewrote 25 as 5 squared and applied the power rule. Then we used the product rule to combine the sequence of powers in the numerator. We calculated the sum of the arithmetic sequence from 1 to 20 After simplifying both numerator and denominator, we applied the division rule of exponents. Finally, we calculated the resulting exponent to get our answer, 5 to the power of 280. This problem showcased several important properties of exponents: the power rule, the product rule, and the division rule. It also demonstrated how recognizing patterns like arithmetic sequences can help simplify complex expressions. Let's look at our example. We need to calculate the value of 5 to the power of 2 raised to the power of 3 squared, divided by the quantity 5 squared raised to the power of 3. Let's solve this step by step. First, let's start with the innermost exponent. 3 squared equals 9. Next, let's calculate 2 to the power of 9. This equals 512. Now, let's work on the denominator. We have 5 squared, which is 25, raised to the power of 3. Using the law of exponents, we can simplify this as 5 to the power of 2 times 3, which is 5 to the power of 6. Next, we need to calculate 5 to the power of 6, raised to the power of 2. Again, using the law of exponents for power of a power, this equals 5 to the power of 6 times 2, which is 5 to the power of 12. Now, we have 5 to the power of 512 divided by 5 to the power of 12. When we divide powers with the same base, we subtract the exponents. This gives us 5 to the power of 512 minus 12, which is 5 to the power of 500. Therefore, our final answer is 5 to the power of 500. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.